Hey, Wheat North, Mr. Yergler here. In calculations involving equilibrium, there's what's called the reaction quotient, which is referred to as Q. This video is going to go over how to calculate that and how to use it. Here's a generic graph showing equilibrium. We've seen this before. You can tell what the products and the reactants are just by the shape of the curve, right? The red line is decreasing, so that must be our reactants. The blue line is increasing, so that must be our products. And we talked in the first video about how to calculate K, and that is products over reactants, right? So just looking at the graph without knowing anything else, is our K for this particular situation equal to 1, greater than 1, or less than 1? It should be greater than 1 because by the looks of the graph, at equilibrium, which is at this point here and beyond, our concentration of our products is greater than our concentration of our reactants, and so our numerator is going to be bigger than our denominator, so it's got to be greater than 1. Now the reaction quotient is calculated actually the exact same way that K is calculated, but it's not the same thing. It's for use when you're not at equilibrium. So K is only useful when you know that you've reached equilibrium. But a lot of times it's necessary to calculate what that ratio of products to reactants is at a different point in time, right? So you could calculate the initial conditions, you could calculate right here, or you could calculate anywhere in between. At any point before you get to equilibrium, you can calculate Q. And then by comparing Q to K, we're able to figure out which way the reaction is still needs to go in order to reach equilibrium. So just looking at this right now, at our initial conditions, is Q large or small? We start out with a lot of reactants, and we start out with virtually 0 products in this graph, and so our Q would be extremely, extremely small, right? A really large denominator with a near 0 numerator. What would Q be equal to at this point in time? Q would have to be equal, at this split second, our concentrations of our products and our reactants are equal, right? So it would have to be 1. Imagine sliding this blue line over. Your Q is getting closer and closer to K because your concentration of your products at this point is very close to the concentration of the products at equilibrium. So if Q is less than K, we still have to create more product. If Q is equal to K, the system's at equilibrium. If Q is greater than K, then we're not at equilibrium. We have to make more reactants. And I don't want you to memorize this. I want you to understand it. Okay, so think about it mathematically. If Q is smaller than K, which is the case on our graph, we still have to produce more products, right? If Q is small, that means that our numerator is also small, right? Our numerator is products. And so in order to bring Q up to match K, you have to create more products. If Q is greater than K, which doesn't appear on this graph, that means that our numerator is larger than it is when we're at K, right? And so in order to reach equilibrium, we're going to have to decrease some of our product and create more reactants in order for Q to come down to where it matches K. Now I said that kind of fast. It might be helpful to kind of rewind now that you have it written down and just kind of follow with me verbally as I go through this. Calculating Q allows us to figure out which direction the equation, the reaction, still needs to go in order to reach equilibrium. Okay, this is really helpful when we have a mixture of gases in a container, for example. Okay, and here is an example just like that. If we're producing ammonia from nitrogen and hydrogen, we're given a temperature. The temperature actually doesn't really matter, but it is important that it's at a specific temperature because equilibrium is temperature dependent. But we're given an equilibrium constant. If these are our starting concentrations, then figure out which direction it needs to shift, or the reaction will shift, in order to reach equilibrium. So the only way to do this is to kind of figure out where we're at on the graph, so to speak, figure out what is our current ratio of products and reactants, and then compare that to what it will be when it's at equilibrium, which is what we're given the equilibrium constant for. So these are all of our initial conditions. This little 0 indicates initial. And so set up your Q equation, products over reactants. Remember to square ammonia and take hydrogen to the third. Plug in your values that you're given, and you solve the math, and you get this answer. Now this is a relatively large answer. Now we need to compare that to our equilibrium constant. Now again, don't memorize what needs to happen in different cases. Just think about it. Our numerator, if this is a larger number, that means our numerator must be larger. If our numerator is larger, then that means we have a lot of product, right? In order to reach equilibrium, we're going to need to get rid of some of that product and shift it back to reactants. When we decrease our numerator, now our ratio of products to reactants will decrease and eventually reach equilibrium. So Q is greater than K, and so the reaction will shift left. You go ahead and do this one on your own. Start by calculating Q, and then compare that to K, and then determine which direction the reaction still needs to go in order to reach equilibrium. Bring that to class. Bring any questions you have about this to class. We'll get a little bit more practice there. And this is Mr. Yergler signing out.